My presentation is on Cellular Automata. So you start off with like a simple pattern like this on a grid. Oh no, I did have a picture but it must have vanished. Okay, for each cell you have its neighbourhood, which is so like if we take this black box, that's like everything in a square around it. And so the rules are, if it has exactly three, if any cell has exactly three black neighbours, then it gets born, which means that it turns black. And if a cell has 2 or 3 neighbours, then it stays black. But if it has less than 2, then it dies, so it goes back to white. And with overcrowding, if it has 4 or more neighbours, then it also dies and goes back to white. So when you start with a pattern like that, you get some stable forms, which are forms which don't change, or which change between like 2 different patterns. So here's one called the blinker, which, as you can see, just switches, but it because it's a stable form, then it doesn't do anything else, it just stays like that. And then there's also the beehive, which is slightly more interesting. So as you can see, it does a couple of changes and then it ends up like this, and it will just stay like that forever because that's stable. And then there's also this one, which is really cool. So this is turned into a set of 4 blinkers that just keep going forever. And then there's the slightly more interesting patterns. So what it appears, this is a glider, and it goes across the screen forever until it maybe hits something, and it goes at a 45-degree angle. But you could potentially make like a computer out of this if you had a stream of gliders as the input, and then you can do things to it to create logic gates. Like you could do a NOT gate by firing gliders at it, and then if there is one, then they collide and disappear. But if there isn't one, then you like add an extra glider. So yeah. So that was 2-dimensional cellular automata. You can also do it in 1 dimension. So you start with just one like black right in the middle of the top of the screen, and then you have a rule set like this. So what you end up with is like a triangle because it goes down each line, and it applies a set of rules like this. So this is an interesting one. It's called Rule 90 because that's what the binary under it, that's what the number is. So you can see it forms the Sierpinski triangle, which is really interesting because you've just got a simple rule set, but by keeping applying that rule over and over, then you get something incredible like this. And then there's Rule 30, which again, it's because that's what the binary says. And this one is actually completely random, so it's often used as a random number generator. And that's also really interesting because, again, you've got like a rule set, so you think that it would follow some kind of pattern, but it's completely random even though you've got a set of rules. And similar patterns are actually seen in nature, like on this shell. So the uses of cellular automata, they can be used to model lots of things like bacteria or traffic or city growth, because stuff like that will follow similar rules, like with the loneliness and overcrowding and stuff. It can also be used for cryptography, so the Rule 30 is used as like a random number generator in cryptography. It can also be used for prime number generation. You can set up a really complicated 2D cellular automata program that actually works like the sieve of error stuff thingies.
Yeah.
To get all the prime numbers. And you can use them in computers, like in memory chips and stuff, to make storage easier. And some people also think that the universe is a cellular automata and are looking for like a starting set which will then turn into the universe, but I think that's a bit strange.
Yeah. Interesting philosophy and all rest overlap there. Yeah.
The end.
Thank you.